My name is Andrei Kunkov, and I have the great honor to serve on the scientific advisory of the Clay Mathematics Institute. And as we were planning this 140th of a millennium celebration, we couldn't really think of any better person to speak about P equals versus NP as Avi Wigderson from the Institute of Advanced Study. And of course, we're very much not alone in this thinking, as evidenced by Avi receiving every imaginable prize and professional distinctions for his work on computational complexity. We were only hoping that the circumstances will allow him to come and give this lecture. As you can see, he's here. Our wish has been granted, and so please welcome Avi Wigderson.
Hi everybody, I'm really glad to be here and talking to you about this Clay Millennium problem. The plan of the lecture is simple but dense. This is what they asked me to do, to state the problem, to explain the meaning, to tell about the history and of course progress. I'll talk about progress in many ways, about new directions that this problem led us to, new notions we defined, connections we made, techniques we had, which revealed lots of structure about the problem and the computation in general. Also led to a very robust methodology for this field of computational complexity. So you'll see that we know a lot. I'll tell you a lot, maybe too many things, but luckily I'll switch context a lot, so if you didn't follow one thing, you'll recuperate immediately. But we know a lot, but I think, there's much more that we don't know, as will be evident. Okay, so let me start. Statement of the problem is really simple. Think of the following task. I give you a map, planar map, like in geography book, and ask you whether the countries can be colored by three colors, let's say red, green, and blue, in such a way that if two countries are adjacent, they should get different colors. So that's very basic. The question is, what is the best algorithm for this task? And the P versus NP question can be stated extremely simply, asking whether this task has an efficient algorithm, a fast program. Here I mean a fast program for every input, for every map. And fast would mean just polynomial time in the size of the map. So the whole question boils down to understanding just one simple stated problem. So again, here we demand an efficient algorithm which for us will be polynomial time in the size of the input. That's where P comes in. Just note that an exponential time solution is trivial. You just try all possible colorings, but of course this is too slow. The NP comes from the fact that this problem has simple verification. If you give me a coloring, I can easily check whether the coloring is legal. The if and only if there says that this question about complexity classes P and NP reduces to just understanding this simple problem, and we'll talk about NP-completeness later. And I want to point out that complexity is a very fragile notion, very sensitive notion. The same problem, if I ask you, can the map be two-colored, has a very simple algorithm, just a greedy algorithm. The question whether it can be four-colored is even easier. You always say yes. So somehow three coloring sits in some sweet spot. What's the meaning of this question? Well, I want to give you a philosophical answer, and this will be easy to remember if you don't remember anything else. This is a universe, but for us the universe is made out of problems. So it's a universe of problems, and think of NP as all the problems that we, as humanity, want to solve or understand. And inside it sits P, which is all the problems we know how to solve. Okay? And the basic question of P versus NP, and this I should state philosophically, is not just computational problems or mathematical problems. Is the Riemann hypothesis true? but also can we cure cancer or can we understand how the brain works? So given that, and given this, the way I define these two galaxies, these two collection of problems, obviously, asking whether P equals NP is really the question about the limits of human knowledge. So this is how I think about it. But we will go back to math after this philosophical point of view. But I want to justify just a little bit why is NP the problem that we want to know, and no more than that. And the reason, I'll give you a caricature of how I think, or you may think, about some of our professions. Like a mathematician is searching for something. What? Proofs of theorems. Scientists usually are given some data and they are searching for a good model to explain the data. Engineers are given some constraints, building a bridge with some costs and some materials, and are seeking a design. In all these and many other intellectual pursuits, I claim that checking whether you got where you wanted to should be easy, right? Verifying that you found what you wanted should be doable. I mean, otherwise, who would start on a task that you cannot even recognize if you ended it? So these are NP problems. And so, in this sense, if P was equal NP, we'll have an automatic quick answer to any problem like this. Would be sort of utopia, and maybe that's one reason why people believe that P is different than NP. Okay, but I want to go back to math, and first telling you just in one slide, very brief history of the problem. The history is really millennia old, because algorithms were designed by mathematicians, for 4 millennia. Euclid's algorithm for GCD, Gaussian elimination was invented by Egyptians way before Gauss. But even though these algorithms existed, people used them, and many other mathematicians before computer science was born, were looking for algorithms to solve problems. Something critical happened around the turn of the century, which you are all familiar with, the crisis in mathematics. Hilbert had a dream. His dream was that, we will know, we must know, we will know. So he believed that truth in mathematics is the same as probability in mathematics. And he further believed that if proofs exist, they can be found by mechanical procedure. This amazing, beautiful dream was shattered completely, first by Gödel, who proved the incompleteness theorem, showing the first equation is wrong, and then by Turing, by his undecidability theorem. And why this was critical is that Turing, in order to prove a theorem about refuting Hilbert's dream, had to define what computation was. He invented this Turing machine, which is a formal mathematical model of what an algorithm is, and used this in his proof. Of course, this one consequence is the computer revolution we are all living through, but for us, for computer scientists, mathematicians, this became a criterion of which mathematical problems we can understand. Those that we can, have a decision procedure for, we can. So people started proving undecidability theorems by reductions to the halting problem of Turing. So, for example, word problems in general groups, that's undecidable. Understanding the Alfantine equations in general, that's undecidable. On the other hand, for other problems, people developed amazing decision procedures, like Tarski for the first order theory of the reals, Haken for unknownness, and many others. And the main realizations that came from the algorithms that existed, like these algorithms, the many algorithms for lots of problems that people were trying to solve using these computers that showed up, was that decision procedures, finite algorithms, can be extremely slow. We can never wait for the result. And so complexity theory was born, in which we wanted to quantify exactly how much time it takes until we see a solution. And in the 60s, people developed this notion of P, a notion of efficient computation, something that terminates in polynomial time in the size of the problem. And in the 70s, we saw this understanding that a class of problems we really want to solve, a feature that of many problems we want to solve, is that we can efficiently recognize membership or efficiently recognize that the solution is correct. This was the definition of NP. And in particular, understanding that this class NP has complete problems, which I'll explain, this notion of NP-completeness. It's an interesting historical point that in a Gödel, this was discovered in the 90s, a letter Gödel wrote to von Neumann, who was dying already of cancer, contained lots of the ideas that are in this formal development in the 60s and the 70s. It's really fascinating. But he didn't pursue it. I mean, I guess von Neumann never answered, and he did, as far as I know, he didn't pursue it. I want to just stress that these choices made in the original papers, choice to work on worst-case analysis, so having an algorithm for every input, the choice to allow the freedom of polynomial time as maybe as opposed to linear time where it's really efficient. So this flexibility and these choices were extremely prescient, and they allowed the uncovering of structure, only after which we could go back and fine-tune the notions of efficiency and other notions. So we want to understand whether P equals to NP. We have to understand what this class of problems is. And I'll give you many ways of thinking about NP throughout the talk. So first, let's take a look inside this class. And we know many problems who are in P, namely problems for which fast algorithms exist. These are the problems that you have in your phone apps. And on the other hand, many problems. I mentioned map coloring, and theorem proving is another example, which are NP-complete, by which I mean hardest in the class of problems in NP. I'll have a more formal definition. And we have lots of other problems where we don't know, like integer factoring. It's somewhere. We don't know whether it's in P. We don't know if it's NP-complete. So let me formally define what we are doing in this completeness notion. The fundamental definition is that of a reduction. We just put a partial order of the class of all computational problems. We say that A is less or equal B if solving B is not much harder than solving A. Or maybe I did it in the opposite direction, but this happens in every class you teach on reduction. And then you can say that a problem in NP is complete, is universal, if for every other problem in NP, is easier than that in that sense. So it's the hardest problem in NP. And you can imagine, although I won't talk about it, that finally the first NP-complete problem was the most non-trivial one, because you have to prove for every other problem in NP that it reduces to it. And after that, you can make reductions from this one complete problem. So as from the definition, you see that NP-complete problems are all equivalent. If one is easy, then all of them are easy, they are interreducible. If one is hard, then all of them are hard. So any one of them captures the complexity of P versus NP, and if you want to prove on this, to work on this problem, you can choose your favorite and try to find an algorithm for it, or try to find that there is no algorithm for it. And we know map-free coloring and theorem proving, which I'll maybe clarify what I mean there, are NP-complete, as we know. And integer factoring, for example, is one where we don't know the complexity of. So a little more precisely, what is a reduction? I'll just give you an example between theorem proving and map coloring. It may come as a shock to number theorists that the Riemann hypothesis can be coded as a map coloring question, but this is basically, in fact, a pretty simple result. A reduction is simply an efficient algorithm, which we know, A, and it does the following. If you give it a claim, like the Riemann hypothesis, plus I demand some bound on the number of pages in which you are going to give me the answer, because above 1,000 I will not read it, then this algorithm transforms the claim into a map in such a way that the claim is true if and only if the map is three-colorable. And moreover, if anybody has a formal proof, this algorithm would convert it to a three-color. So that's the reason you might as well work on the map coloring of this map if you want. This is A is basically a reduction in this initial papers, Cook-Up and Levin. Okay. Something that is a bit of a diversion, but is really important, is the ubiquity of NP-completeness. I don't know any other mathematical notion like it. What do I mean? So by now we know thousands of NP-complete problems. It's a triviality to prove, when I was doing my PhD, it was still proving NP-completeness of a problem was still a paper, but this was many years ago. Anyway, but NP-complete problems appear not just in computer science and math, but they appear in biology, physics, economics, and so on. And it's sort of amazing that this computer science notion appears even in the title of hundreds of papers across the scientific field. So I don't think there's any other mathematical notion with this property, and you have to wonder why. And one explanation is a very important point of view on what computation is in general. And in the beginning, since Turing, we thought about computation as an evolution, of a simple, sequence of really simple local operations on bits, sequences of bits. But this was then, and by now, we realize that, you should think this way about, evolution of, maybe distributed systems of computers, but much more. Lots of settings in nature, neurons in the brain and atoms in matter and, prices in markets, and I will not read the whole list, friends in Facebook. These evolutions happen locally and simply, and, they create, really weird phenomena. This is important because it explains a lot of, I think, one of major contribution of complexity theory, which was born out of the previous NP question, on the interaction and collaboration between theory of computation and the sciences. This is sometimes called the lens of computation on the sciences. And what it means is that the know-how of computational complexity, some of the methodology, and computation itself should be integrated into models of nature. Probably the resources are different than time and space, but essentially the same type of thing happens. There's another point I want to talk about, which is the diversion. I stress that previous NP is defined for worst case computation. And lots of people react to this by asking, something is wrong, because as we see, NP-complete problems are not really hard. What do I mean by that? One is, nature solves them. So you think of problems that their formulation is NP-complete, like protein folding, minimal energy, or the minimal surface area of the way forms are folding, or in economics, the way strategies of agents in strategic games are forming, maybe by the market somehow. It seems like, these things happen. So somehow NP-complete problems are being solved by nature, and nature apparently is an efficient algorithm as well. Similarly, in algorithms for problems that are NP-complete, not just nature solves protein folding, probably that there's an AlphaFold program. The originators won the Nobel Prize because their learning system is able to predict practically the three-dimensional structure of protein for almost all proteins. Similarly, there are SAT solvers. So SAT is checking whether a formula has a satisfying assignment. The most basic, in fact, the first NP-complete problem found is a very important problem because you can translate any other problem into it. Of course, people translate problems like checking whether their software or hardware or protocol work need to be solved. You want to check something before you release it. So people developed algorithms to solve these satisfiability problems, and they seem to do tremendously well. They solve problems, regularly in seconds, even if these problems have millions of variables and constraints. So again, it seems that in practice you solve NP-hard problems. This is a problem in P, but nevertheless, one of the earliest examples, linear programming, before it was known to be in P, it was noticed that the simplest algorithm was the very first algorithm existing by Danzig from the 40s. Will run in linear time and essentially any linear program you give it, but we know that the worst case for this problem is exponential. So basically, this is another field of study. I'm not going to talk about it, where we do study average case complexity on a variety of distributions of inputs. And LLMs, of course, show us that many natural distributions, we can solve hard problems. So the challenge is really understanding what are natural distributions, and this is part of the challenge of understanding how far AI will go. In particular, what is the distribution on theorems we are interested in proving. But the rest of the talk, I'm going to go back to the original formulation, talk about the P versus NP in the worst case sense. Okay, so the first question to ask is what are the possible resolutions of the problem? Of course, one is that they are equal. This is the utopia I mentioned, but I should mention a caveat also, because if P equals NP, there are no secrets. So there is no cryptography and no online shopping if you want your privacy. And anyway, this direction towards proving P equals NP is just developing good algorithms, and that's a huge field. That's the main production of theory of computation. P different than NP is another possibility, of course, and that the way you do it is try to prove hardness, try to prove that there is no efficient algorithm for a problem in this general model or maybe restricted models. Another part of, and you'll see examples, is utilizing hardness. Turns out the hardness is not only bad. And we see, basically complexity theory is about uncovering structure in this world of computational problems, especially inside NP, but also outside. But I want to point out to a third possibility, a third outcome that I'm not sure is covered by the $1 million prize, that this problem is independent of set theory, or it's quite possible. And also this is a field of study. And there were some talks in the complexity workshop about trying to go towards it, maybe by proving weak independence results, like from fragments of arithmetic. And that has to do with a field I will not talk about, which is called proof complexity, and aim more at the difference between NP and co-NP. Right, so there are three possible outcomes. Okay, let's go back to our picture of this universe. I want to talk about this gap between P and NP complete. We saw integer factoring is a problem. We don't know its complexity. We do know, it's a famous theorem of Ladner from the 70s, that if P is different than NP, there are infinite problems in between of growing difficulty. So an infinite chain of problems, each one super polynomially harder than the other. So this dark area in the middle is like dark matter in physics. I mean, these problems should exist. We should see them all around, but we don't. I mean, we know very few natural problems lying in this gap. So we have to understand it, and this is the topic of the next two slides, is this understanding this dark matter. So where is it, or does it exist? And dichotomies are about types of problems which actually only live in P or NP-complete. So I'll exemplify this. So one on constraint satisfaction problems, this is a wide class of problems, and these are most natural problems we meet. I showed you one. This is a three coloring. So I want you to think about it as a system of inequalities. You assign a color to every variable, to every country, and you write this system which the variables take values in the three different colors, and I tell you which pairs are supposed to be different. These are adjacent countries. This is one type of constraint satisfaction, so all constraints look alike. Another one is this satisfiability problem. Here a constraint is just three such, so each constraint is three Boolean variables, negated or not, and you want to satisfy all of these constraints. Things you are maybe more familiar with are, linear equations. Let's say 3 lin, it means 3 variables per equation, but these are just linear equations. Let's say modulo p, think of p some fixed prime. That's one example of linear equations. You can also ask, it's about 2 variables per equation, and we'll see that this is, interesting to distinguish between them. Anyway, this is a collection, you can imagine the collection of all constraint satisfaction problems. Again, most problems we tackle have this form. So what do we know about this? I want to talk about this dichotomy theorem. So think about all these constraint satisfaction problems. They are specified by a relation which tells you what these equations or inequalities should satisfy. They are of some arity, k, and over some alphabet, some domain, d. And you are given a list over n variables, you are given a list of constraints, and you want to solve it. So basically, the decision is, can you satisfy this system or not? And as I said, it captures numerous problems. And we know that the examples I showed you before, some of them are in P, and like solving linear equations, of course. 2 coloring, I mentioned, is easy, 4 coloring. And others are NP-complete, so this is known. And a very bold conjecture at the time in the 90s was that every constraint satisfaction problem has, is either easy or is NP-complete. And it took, some 20-some years, but we have a dichotomy theorem today. So this explains partly this, dark matter not existing, at least if we call natural constraint satisfaction problems. And it's very interesting in many ways. It involves both, algebra and logic, and of course, algorithms complexity. There's a very simple criterion which will tell you which are the hard ones. You just look at the relation, and you can tell which are hard and which are easy. And one interesting outcome is that even though you could think that each of these problems may have different specialized algorithms, the easy ones, it turns out that really Gaussian elimination is at the bottom of all of the easy ones. There's also one reduction in the case of hardness. So it's quite surprising, I think. There's a more, let's say, complex dichotomy which talks about not decision problems, yes, no, but rather approximation problems. And this is very important. It goes by the name of the PCP theorem and its continuations. So again, we have the same type of problem as before. We have some constraint satisfaction problem. And the decision problem, we just want to know whether all can be satisfied. But the optimization problem, problems that are hard don't go away. This is the effect of life. And so we try to do what we can. And one natural thing is, if we can solve all, if we can satisfy all constraints, we ask, how many can we satisfy? And can we approximate the number of the constraints we satisfy? What percentage can be satisfied? And we look for approximation problems, the best possible for each one of them. And now it turns out that people, of course, are doing that. And for one problem, they get factor of 2 approximation. For another, they have factor of 100. For another, they have a factor of, I don't know, square root n. So the world is much murkier, much more complicated than the world of decision problems. And nevertheless, this theorem, this PCP theorem, which I cannot state its importance, from the early 90s, says that we can still prove hardness of optimization. So basically, it stated that approximating the fraction of satisfying assignments, let's say in satisfiability or coloring, is NP-hard. So it's not just NP-hard to decide if all are satisfiable, but it's really hard to approximate, let's say, up to 1% the fraction of satisfied assignments. And once we have this, once we have a handle of hardness, the next question, of course, can we determine exactly how hard each one is? And for example, look at 3 satisfiability. These are disjunctions of 3 variables. So clearly, if you randomly pick values, 0, 1 values, 7/8 of them, with probability 7/8, you'll satisfy each particular clause. So you can satisfy 7/8. And it turns out by a very important result of Hasselt that satisfying just an epsilon more for any positive epsilon becomes NP-hard. What another thing it proves is that for this 3-line problem, linear equation mod p with 3 variables per equation, it has the same property. Here you can satisfy 1/p, just randomly pick an assignment, and it proves that satisfying just a bit more is NP-hard. It's a question, you can try to go further. You can say, can I distinguish between whether I can satisfy half, close to half, or close to 1? I promise you that either this or that. It's a conjecture, but a very important conjecture called unique games conjecture, that this too is NP-complete. And if it is, this leads to an understanding of all these approximation problems. It's a result of Raghavendra. It says that under this assumption, under this assumption, there's always, for every relation, there is a constant that tells you the threshold between easy and hard. So on the one hand, it's easy to satisfy this constant fraction of equation, theta bar. On the other hand, to satisfy a little bit more is NP-hard. So this gives a complete understanding of all these approximation problems. And again, amazingly, this really works. I mean, the algorithm for all of these is really one algorithm, and it's called the sum of squared optimization technique, which really goes back to Hilbert's 17th problem, which is about sum of squares. Okay, so these are dichotomy theorems. I want to talk, just in one slide about another connection of P versus NP that took us all by surprise in some sense. You all know about probabilistic algorithms. These are algorithms that toss coins. There are numerous problems for which we know fast probabilistic algorithms, but in many cases, the best deterministic algorithm that doesn't toss coins, requires exponential time. So it seems that randomness is extremely powerful in algorithms. That's what we used to think, and there are many such algorithms in math. I listed some here, and there are, of course, many others for lots of other problems. And then we got better sense by this following theory that developed over some decades. It started actually from cryptography, which led to trying to understand randomness in cryptography. And the upshot of this result is that if you believe P is different than NP, and I put it in quotes because you have to believe in something a little different, but of the exact same nature. So you have to believe that the natural problem is difficult. If you believe it, then randomness is useless for algorithms. Every probabilistic algorithm that you have or you don't have that's efficient can be replaced by essentially an equally efficient algorithm that uses no coin tosses. Okay, again, randomness cannot help in speeding up algorithms. So that's another tells us something else about NP we didn't know about this question. Because NP connects to the theory of pseudo-randomness, and this is sometimes coined the hardness versus randomness paradigm. So hardness, computational hardness, can be traded for randomness. Okay. Now I want to talk about a very different and actually beautiful story of, in the last 30 years or so within the complexity theory, and how this field changed by trying to understand NP as proof systems, going to inventing new proof systems. What are proof systems? I mean, the math is full of proof systems, but they all have the following common features, right? I mean, true claims should have proofs, false claims should not, and equally important, verification of proofs or candidate proofs should be efficient. If it was not, then this proof system is useless if we cannot verify proofs that are given to us. And this can be, let's say, polynomial time. So I want to tell you about the first of several such new proof systems. And these are going to be probabilistic. This will be a place where randomness does help. Probabilistic interactive proofs, and I'll demonstrate what it is by comparing it to what we know and love, NP proof systems. These are, you can always think of NP or any proof system in mathematics as a situation where you have two entities, one is a prover and one is a verifier. There's a claim, Riemann hypothesis, known to both, and the way you are convinced by that the claim is true is the prover may be an infinite powerful mathematician in the audience, writes a paper, and then the verifier, the referee reads it, and it has to accept if it's correct and reject if it's not correct. So that's a normal classical proof system, where the verifier is efficient, of course, but is a deterministic algorithm, and this soundness and completeness hold always. IP, interactive probabilistic proofs, look the same, only you allow the verifier to toss coins. So we are changing the notion of what does it mean to prove a theorem. The verifier can toss coins, and it can make mistakes. The mistakes can be made arbitrarily small, but they are allowed. So this seems somehow sacrilegious. We are taking a notion of mathematical proof and allowing errors. This is terrible. Of course, this came from cryptography. In the second paper, the motivation was proving statements about, the way you choose your secret keys, let's say, where it's not like about the Riemann hypothesis. So it is reasonable to allow errors, but also we know with some mathematical papers that were refereed, there also can be errors. The other thing we allow is instead of just writing a paper, we allow an interaction between the prover and verifier. So, the verifier can ask questions, can toss coins and ask questions, and only after that decides whether to accept or reject. So there is an interaction here. And you can ask always with any computational model, including this one, whether it's reasonable or not. I think that, we pursue also unreasonable definitions, models like all of you. But this is extremely reasonable because if you think about the way we do math, right, we talk to colleagues and we, exchange ideas and ask questions, etc., or in a classroom, But I want to say that it's not just reasonable. I want to stress that this is really a revolutionary scientific and mathematical notion. I will not, it's a different talk altogether to demonstrate this. What I want to talk about is more proof systems. Once we had this notion, we started dreaming up, and for a reason, other proof systems. One thing that happens when you allow this type of proof system is that somehow magical properties can be obtained that cannot be obtained by normal proof systems. I'm sure some of you know about zero-knowledge proofs. So in this model, I can convince a clay foundation that I solved the Riemann hypothesis without giving them a shred of evidence of how. In fact, I can convince them that I solved one of the remaining 6 problems, and they will not even know which, but they'll be convinced that I did. Anyway, we generalize this to allow even weirder proof systems in which, let's say, we allow 2 provers. In this model, a verifier can talk to 2 provers who may have colluded in advance, but once he starts talking to them, they do not communicate. And he asks questions of both, and they're, again, trying to convince him of a claim. And again, this should be correct, soundness and completeness have to hold with arbitrarily high probability. And you might think, I will not explain why we introduced this, but you'll see consequences of this shortly. And once we keep dreaming up things and we do randomize, why not allow quantum computing? If we allow quantum, we think about quantum computing, might as well consider quantum proof systems, and we do. And there are analogs of the one-prover model and the many-prover model. These 2 can be 3 or 4, etc. And the question is, what do you gain? Well, we seem to be gaining the ability to prove more and more theorems, and it's sort of amazing. Within the span of a few years, all these proof systems were completely understood in terms of the computational power of what they can prove. Let me leave this. It is reasonable if you think about the police interrogating 2 suspects of a crime. And there are many other reasons to see why it's reasonable, but we'll see why it's good to think about this model. So this avalanche of characterizations, exact characterizations of these proof systems followed within a few years. And we know, for example, that these interactive proofs with one prover are exactly the problems we can solve in polynomial space. We know that what you can do with 2 provers is exactly what you can do in non-deterministic exponential time, the exponential analog of NP. And this, and so on. And it's really interesting that these, we like acronyms in computational complexity. This is terrible. I always think that the physicists have a much better, PR, naming their problems, dark energy or black holes or red stars, red dwarfs, I don't know. We have these terrible names. Nevertheless, they all carry really strong conceptual meaning. For example, IP equals P space really mean, or one of its consequences, is that if a Martian landed here tomorrow and claimed it has a winning strategy for chess, we can check it. Even though there is not just one quantifier, it's not like mate in one. I mean, this is an alternation of quantifiers, it's a game. Nevertheless, we can check it by interacting with this Martian. Check that they have a winning strategy. It's sort of amazing. And many others have such consequences, and I'll talk just a little bit about 2 of them. This characterization of NP, we'll be back to it. And this later thing which characterizes the 2-prover quantum version interactive proof as capturing the class RE. This is a class of recursively enumerable problems. This is a class containing or defined by the halting problem that Turing did. So these undecidable problems, uncomputable problems, can be checked in this proof model. This is sort of an amazing result, and I'll tell you about it in a second. Let me tell you what PCPs are. It's another model, but in fact it's a version of the two-prover classical model. You wouldn't recognize it, but turns out to be the same. So here's NP again. This is a standard NP. And PCP is another model that looks like this. It's not interactive. The prover just sends a message to the verifier. The only constraint, the only thing which changes is that now we add a constraint. So now the verifier is probabilistic, but the verifier can only read, let's say, 20 bits of the proof. So imagine how you can find a bug by sampling the proof and 100-page proof and reading 20 bits of it. So this seems like it cannot, nothing can be proved in such a system. However, the PCP theorem says that these two are equivalent. If you have a normal mathematical proof, you can convert the proof, in fact, efficiently convert the proof, into another proof, which can be verified by random sampling with very high probability. How high, it depends on this 20. I mean, if you want better, this will give you 99% assurance. If you want 999, then maybe you have to ask 100 bits. But it's independent of the proof length. So I want to talk about the meaning of this. Of these two things, and then, yeah, good. One, consequence of this PCP theorem is, that referees can check papers in, a minute and then, go do what they really want to do. This was never implemented, of course, so the really important consequence is what I mentioned before, is this understanding of optimization problems. That was the starting point. And there are many other things I did not talk about, effects, error correcting codes. There's many practical applications. People actually sort of implement versions of it. So it's a very powerful and important theorem. What about the, this weird thing about quantum interactive proofs with two provers? It seems like, we are playing games in our sandbox and, generating weirder and weirder proof systems, and no wonder we get to do undecidable problems. What is this complexity theory game? But it turns out that this is an extremely important result for math and for physics. It turns out consequences of this theorem, some of you I'm sure know, are resolving in the negative some major conjectures. So in von Neumann algebra, the famous quantum-embedding conjecture turns out to be wrong. This demonstrated. In quantum information theory, there's a Tilson problem about comparing types of measurements. Let me not go into this. Anyway, there are mathematical conjectures being proved wrong by this, and moreover, once we know that, it turns out that this kind of techniques embedded in these arguments, which this is a 200-page paper, and all the background can be used to resolve or resolve in the negative in this case. Others, like the Lyons-Aldous conjecture in probability theory, was just recently refuted using techniques like that. So these games lead to somewhere in this methodology of the field, which tells you to continue, or math, continue your aesthetic run is more than justified. So the last 10 minutes, I think I'd better talk about really trying to prove hardness, the little we know about it, and the excuses we have for it. So Turing started us off really nicely because he gave us a lower bound technique. He proved that something is impossible, so that's a lower bound. The way he did it is using, this simulation and diagonalization argument and for Turing machines. And this technique can do some things also in the finite, in the complexity theoretic world. For example, it can show that if you have more time, you can compute more functions. Okay, that's very important, the time hierarchy theorem. You can prove a version with more combinatorics, can prove more version of a small version of the P versus NP problem. So the linear time version of P versus NP is in fact proved, right? So this result. So you might ask yourself, what's the problem? We can use this technique to prove P different than NP, and Baker, Dean, and Solovey realized that this technique alone will not suffice. So that's a barrier result. What does it say? It says that if we use this technique, whatever we prove for some machines will be the same if we equip these machines with an oracle, namely an ability to query the answer to a specific function. And because of that, I mean, you can now show why this technique will not suffice, because you just have to exhibit oracles, functions, which resolve P versus NP in two different ways. So this cannot be enough, and that's one barrier result. To explain why this technique is not enough. Okay, so if this is not enough, we need to do something else. And the combinatorial approach to lower bound tries to make things finite, talk about finite objects. It's very simple to take a Turing machine, which is computing some function over strings, over inputs of any length, into a sequence of circuits, Boolean circuits with Boolean operations on finite functions, one for every length. Okay, and in fact, it's very easy to see that if the Turing machine runs in time t, then the sizes of these circuits, T of n, sizes of these circuits will be roughly the same size. So we can try to argue about these finite combinatorial objects, prove circuits or bound. And it should work because we know, just by a counting argument, that if you look at a random function on n bits, it requires exponentially large circuits. It's just simple counting. And the challenge is to find an explicit function, like satisfiability or coloring, or one of these that requires just a polynomial lower bound. This will prove already P different than NP. But I want to stress that little we know, we cannot even prove superlinear lower bound. We cannot prove lower bounds bigger than 5 times the input size. So that's the state of the art there. Of course, then we do what everybody does. We try to prove lower bounds against circuits that have their hands side behind their backs, and we take out their eyes and so on. And one model for which this was a breakthrough result is a monotone circuit, circuits that do not allow negation. In the 80s, proves that this requires exponential time. Monotone functions like the clique, whether a graph has a big clique, a big complete subgraph, requires exponential size monotone circuits. That's one restriction. Another restriction is asking that the circuit will be very shallow. It will solve the problem fast in parallel. It's the AC0 class. And people found that even the parity function, just whether the number of ones is even or odd, is hard for these constant depth circuits. Okay, so parity is hard. Maybe we add it to the model and allow the model also to compute parity. It turns out for these are also lower bounds, exponential lower bounds were found. For example, for if you allow mod p, then try to compute, allow mod 2, it's hard to compute mod 3. Also, the majority function, whether there are more ones than zeros, is exponentially hard in this model. And really amazingly, when you generalize this, the gates, we allowed mod p, we allowed mod prime. If we allow mod 6, which is a product of 2 primes, then we have no idea about some simple problem like majority probably cannot be done in this model, but we don't know that. And as far as we know, NP can be, all of NP can be done by this model. So it's pretty ridiculous how much we don't know, or another way of saying it's a hard problem. But still, there's some progress with this. Before that, let me tell you why. Well, what kind of excuse do we have for not making more progress in this direction? And this is a very different type of barrier. It's called the natural proof barrier. The techniques used for the lower bounds I mentioned are very sophisticated combinatorial arguments and probabilistic arguments. And what they realized, Rasbov and Rudish in the 90s, is that all these lower bounds fall into a framework that's very easy to describe. They have two features. One, when you prove a lower bound, let's say on parity or majority, you already prove the lower bound for half the possible functions. So this is largeness. So, and the other is constructiveness. The functions for which you prove hardness are easily recognized. If you give me the truth table, I can tell you whether it's hard in this sense. And somehow they showed that all the lower bound proofs as well known actually have this property or can be made to have this property. So now, what's the problem? What's the problem proving natural proofs? Well, it turns out they also prove that if you prove lower bound using such a natural method, then you also broke all one-way functions. So in particular, you cannot prove that a one-way function is hard, like factoring, using a natural proof. So this is our excuse for the being stuck here. And of course, the good thing about barriers is that we learn from them. So the field is very introspective. Once we fail, we try to understand why we failed, what's the set of techniques, and how can we sidestep it and maybe find a way around this barrier. And also, this is a way, it turns out, this can be formalized in logic, and this natural proof barrier can be made into a weak independence result. So I want to end the last two slides with different attempts at proving lower bounds, where the way you prove a lower bound is to design a fast algorithm, which is maybe counterintuitive. One is due to Ryan Williams. He shows that, I told you, NP may be contained in these most 6 constant depth circuits, but something just a little bit above it, you allow time to be, n to the log n, then it will not be in ACC. And this is really interesting how it goes. So imagine the satisfiability problem when I give you a circuit from some class of circuits, and I ask you to decide if it's satisfiable. Of course, we can do it by trying all possible inputs. So what you need, according to Ryan, is to improve it a little bit. You just need to find an algorithm that solves this satisfiability problem a little bit faster than 2 to the n. We are not looking for breakthrough. If you have a little bit of a gain there, then you get a circuit lower bound for this class C, whatever the circuits are. And of course, to get his results, he proves that the satisfiability problem for ACC circuits has such a slight gain over 2 to the n. Proving the same for polynomial size circuits will basically prove almost p-different NP. So you just have to design an algorithm. Just tiny bit better than brute force. And yeah, so that's the question. I mean, can an NP-complete, solving an NP-complete problem avoid brute force search? The last one I want to mention, and for several reasons, is the following problem. This is called the polynomial identity testing problem. It's a very concrete problem you can all think about. I give you a matrix which has variables or constants 0 and 1 in it. And think about the determinant. This problem was introduced by Edmonds. So we have a symbolic matrix. And the PIT question asks whether, when we evaluate this determinant, we get a polynomial, of course. Is this polynomial identically 0 or not? That's a computational problem. Now, it's an easy observation that this problem has a fast probabilistic algorithm, right? You just plug random numbers from a small range into the variables, and of course, if it's identically 0, you'll always get 0. But if it's not identically 0, the probability you land in the variety is small. And what's open is whether it has a deterministic algorithm. Of course, we know under assumptions like P different NLP that, but without assumption, all I want is you find an algorithm for, deterministic algorithm for this problem, just this one problem. And Cabanas and Impariato proves an amazing result. If you have a deterministic algorithm for this problem, polynomial time algorithm, this proves exponential circuit lower bound. So it's enough to de-random. Before I told you that hardness implies randomness, now the randomization implies hardness. I mentioned it in particular to mention that this involves going beyond Boolean circuits to arithmetic circuits over fields, and the variant theory of VP and VNP of the arithmetic analogs of P and NP, and the question about the relationships of polynomials like determinant and permanent polynomial, and it connects to in very interesting ways to basic problems in variant theory, representation theory, algebraic geometry, and so on. So it's a way to prove P different than NP. Concluding, as I try to explain the study of, P versus NP, what NP is and what are, this efficient computation is, led us to develop a big theory. Of course, this big theory, the algorithmic theory, certainly extends to lots of settings I did not talk about, online algorithms, parallel algorithms, distributed algorithms, you name it, quantum algorithms. There's a methodology that was developed of modeling and integrating computational efficiency into algorithms, proof systems, and so on. And there are many often unexpected connections between not just computational problems, but also computational models. And beyond it, there's plenty of work that in collaboration between, theory of computation and math and, sciences, and I try to give some examples. So it's an extremely exciting field. I mean, I've been in it 45 years, and I keep being surprised and excited and having fun. There's still a lot we don't know, so we invite you all to join us and help. Thank you very much.